All right, so let's get going on today's meeting. So what we're going to be doing today is we're going to be continuing our look at inferential statistics, but we are going to introduce a new significance test, the chi-square test for goodness of fit, in order to add to our strategies, in order to expand the number of situations that we can use significant testing on. So we finished the t-test, which covered 3 distinct situations. Now we're going to move to the chi-square test, which opens up more possibilities to analyze more data so we can make more conclusions about populations. So again, this all falls under the same branch of significance testing and inferential statistics, where we are developing the tools and strategies to go from a known sample, a sample that we can measure, and then make inferences about an unknown population. So going from knowing things with certainty about a few individuals to inferring things with confidence and with correct logic about the population of individuals, thus expanding our influence and expanding our ability to help others. And today we're going to go through some do it with me demos as we introduce the idea of the chi-square test. And we are going to stick to a very candy related theme for these do it with me demos, because we are going to see how you can test whether the colors of Skittles that you receive in a bag actually fit the claimed distribution of colors in a Skittles bag. So are you actually getting the color distribution that they promise you, or are you getting too many greens or too few reds? And we're going to see how we can do that for a bag of Skittles. We're going to see how we can do that for a box of Froot Loops. And then we're going to see how we can do it for a bag of M&Ms. And then we're going to tie this into a little bit of rock and roll legends when we take a look at the band Van Halen and why did they insist that at all of their concerts there be M&Ms backstage, but not one brown M&M? Were they just rock and roll divas, or was this an ingenious plan to achieve some other goal? So we're going to take a look at that and take a look and use significance testing to test how effective was their secret plan. So all of that and more is scheduled for today when we take a look at chi-square tests for goodness of fit. So we're going to talk about what does the chi-square test actually measure. We're going to go through the hypotheses for the chi-square test, both the null hypothesis and the alternative hypothesis. We're going to talk about the concept of expected counts, which is at the heart of the chi-square test. And then we're going to take a look at how to interpret the chi-squared statistic and the p-value. And spoiler alert, it's a lot like interpreting the t-statistic and p-value from the t-tests, but there's a new distribution, the chi-square distribution, and we're going to see how we can use that to get a p-value and then interpret that p-value. And then we're going to do the promised do it with me demos when we take a look at whether or not you can test if the colors in your bag of Skittles match what was promised by the manufacturer, if the flavors in a box of Froot Loops match what was promised by the manufacturer, and if the colors in a bag of M&Ms matches what was promised by the manufacturer. And then we're going to tie that in to Van Halen and their insistence that at all of their concerts, they have M&Ms backstage, but not one brown M&M in their entire assortment of M&Ms. So why did they do that? And was it an effective way of attaining the goal that they had? All right, so what does the chi-square test actually measure? So when we were taking a look at the t-test, by contrast, the t-test was designed for quantitative variables, for variables where the size of the variable indicated some measurable aspect of the variable. Chi-square tests, on the other hand, are for a categorical variable. So the chi-square test that we're going to use to introduce the chi-squared procedure, the chi-square test for goodness of fit, this uses categorical data from a single sample. So a single sample whose individuals can be placed inside of different categories, and this variable has to have 2 or more categories. So we're going to see this, for example, when we take a look at Skittles. The Skittles has a categorical variable, the color of the Skittles, and that variable has 2 or more categories. They can be green, they can be red, they can be purple, and each individual can be placed in one of those categories. And when you have categorical data from a single sample, you can use the chi-square test measure in order to analyze that data. And what it analyzes is the question of whether the sample distribution in that categorical variable is significantly different than the claimed distribution. So if you are opening up a bag of Skittles, for example, the manufacturer might promise you that there are equal numbers of each color in that bag. And now your question is, does the sample distribution differ significantly from that claimed distribution? So that significant difference is what we are designing this, or what we're going to use the chi-square measure test to determine, because every single bag is probably going to have some slight difference in the number of reds and yellows and oranges that you get. But the question is that difference big enough for you to conclude that the claimed distribution is not actually the truth, that the claimed distribution is not the distribution that is actually being used in the production of Skittles, and that the sample distribution, you can conclude from that, it's so far off that it could not possibly have come from the claimed distribution. So that's going to make a lot more sense when we actually get our hands on it in the Do It With Me demos. So let's continue on with some other background information for the chi-square test. So the hypotheses for the chi-square test, much like the t-test and much like all significance testing, there are two hypotheses. There's the null hypothesis. And the null hypothesis for the chi-square test is that the categorical variable distribution is the same as the claimed distribution. So the null hypothesis basically says there's no difference between the distribution that you have in your from your sample and the distribution that you have in the population. So the categorical variable distribution, the population's distribution, is the same as the claimed distribution. So I should make that a little bit more explicit. Null hypotheses and alternative hypotheses are always about the population. So what it is saying in the null hypothesis is that the actual distribution of that categorical variable in the population is the same as the claimed distribution that somebody is claiming, that is saying that variable has in the population. The alternative hypothesis is just the opposite of the null hypothesis. And in this case, it's that the categorical variable distribution in that population is not the same as the claimed distribution. It's actually different. One of the categories at least differs from what is in the claimed distribution. And actually, logically, if one category is different, then some other category has to also be different to make up for that difference. But basically, the idea is that the categorical variable distribution is not the same as a claimed distribution. What is the actual truth of the distribution does not match up with what somebody is claiming that distribution is. And then from this, we can generate what are known as expected counts. And expected counts are what you would get, the numbers that you would expect to see in each category of your variable if the null hypothesis were true. So the expected counts are the numbers that you would expect. So again, this is a categorical variable. So what we're actually counting in a chi-square test are the numbers of individuals in each of these categories. So the expected counts are the numbers that you would expect in each category if that null hypothesis were true. In other words, what would you expect to see? How many individuals would you expect to see in each category if the claimed distribution was the actual distribution? And those are the expected counts. And what we're going to do when we calculate chi-square tests, and that's going to happen next class, what we're going to do when we calculate chi-square tests is we're going to use the expected counts, and we're going to get the difference between the expected counts and the actual counts and use those to generate the chi-squared statistic. Now, talking about the chi-squared statistic, we're now going to take a look at how to interpret the chi-squared statistic and the p-value. And the chi-squared statistic measures how far the observed counts, the counts from your sample that you actually measured, that you actually observed, how far are these observed counts from the expected counts? And then that is scaled relative to the size of those expected counts. But the important part is how far are the observed counts, the counts that you get from your sample, how far are those from what you would expect your sample to have based on the expected counts from that null hypothesis distribution, from that claimed distribution. And then that chi-squared statistic is going to give us a p-value, and that p-value is the probability of getting a chi-squared statistic as large as or larger than the one that you observed if that null hypothesis were true. So let's take a look at this visually. So we are going to go to our first Do It With Me demo here. And we're going to go to the Staplet. Let me bring this up here. We're going to go to the Staplet for chi-squared distributions. Link in the description if you want to follow along. And what we're going to take a look now is we're going to take a look at the chi-squared distribution. What does this distribution actually look like? And that'll place into context this chi-squared statistic that we have been talking about. So the first thing that we're going to do here is we're going to take a look at, for the chi-squared distributions, we're going to take a look at these degrees of freedom. Let me just zoom in a little bit here. So the degrees of freedom here, chi-squared distributions have at least one degree of freedom. And that's because the degrees of freedom are tied into the number of categories that you have in your categorical variable. So you can have 1 degree of freedom. And if we plot this, you can see that this plotted distribution here doesn't really look like any of the distributions we've been dealing with. It doesn't look like the normal distribution. It doesn't look like the t distribution. This one is very much right skewed. However, as you start to increase the number of degrees of freedom, you'll see that all of a sudden the chi-squared distribution takes on a more bell-shaped distribution here, much like the t distribution or the normal distribution. And it is heavily right skewed. It's skewed to the right. However, it starts to get that kind of familiar look to it that we've been developing our ability to intuitively understand. So the last thing that we have here is we have this distribution, and this distribution is the sampling distribution of every single sample that we would analyze from this particular population in this categorical variable. And this is a distribution that is built up of samples. And then what we can do is we can calculate the chi-squared statistic from a particular sample. And this distribution will let us know how likely was it to get that particular sample from this particular distribution. So for example, if we take a sample and we calculate a chi-squared statistic of 6, we can calculate the area to the right of a value. That'll tell us how likely it is to get a sample with a chi-square of 6 or greater. To get something as weird as 6 or weirder, what is the probability? And we can see that the area shaded here in blue to the right of the 6, that is 64.72% of the area. So not a very unlikely sample. If we got a sample that generated a chi-squared statistic of 6, we would say, well, that would belong to the null hypothesis. That would belong to the claimed distribution, because it's about a 64% chance, 65% chance that this sample that generated a chi-squared statistic of 6 actually came from this null hypothesis population. However, if we got something, a chi-squared statistic that was more extreme, because the observed counts were more different than the expected counts, we might get a chi-squared value of 18. And as we can see up here, that chi-squared value is very extreme. And the chances of getting a sample this extreme from this null hypothesis population is only 2.12%. So it's very unlikely that this hypothetical sample that generated a chi-squared statistic of 18 comes from this null hypothesis distribution. And if there's a small chance that it comes from the null hypothesis distribution, then there's a corresponding large chance that it comes from the alternative hypothesis distribution. And then we would reject the null hypothesis, accept the research hypothesis. And hopefully all of this is starting to sound familiar, because as we're going to see next class, when we actually run some chi-squared statistical analyses, chi-squared test, chi-squared statistic works a lot like a t-test, t-statistic. It's just that it is for a different situation. It's for a categorical variable. All right, so now that we've seen what the chi-square distribution actually looks like, hopefully you're a little bit more confident in the idea that it's just like a t-statistic, just like a t-distribution. So all of the skills that we've been developing for the t-test are going to serve us very well when we take a look at the chi-squared statistic. And now we're going to be able to analyze categorical variables in an intelligent, objective, and rigorous manner. So let's start some of those analyses in that intelligent, rigorous, and objective manner by tackling the really, really pertinent, important question of whether or not the claimed distribution of colors in Skittles is the truth. Do they actually make the right number of green Skittles? And do they actually make the right number of yellow Skittles? Well, how could we ever find that out? Well, the answer is to do a chi-square test. So before we answer that, just a real quickly want to point out the reason we would do a chi-square test on this is because we're looking at a categorical variable. So we're looking at categories of red, green, purple, yellow, and we're counting the number of Skittles that fall into the category of yellow and fall into the category of green. And when you're dealing with a categorical variable that has frequencies or counts in each category, then you're doing a chi-squared analysis. All right, so what might that chi-squared analysis do? Well, for this one, we're going to go to the M&M Skittles Froot Loops staplet. Once again, if you want to follow along, link in the description. And we're going to start off with Skittles. And the reason that I wanted to start off with Skittles is because Skittles has a claimed distribution that says that each color is produced in equal percentages. That is, the claimed distribution for the Skittles is that you have 20% each of red, orange, yellow, green, and purple candies. So the null hypothesis for the population of Skittles candies in the world is that 20% of them are going to be red, 20% of them are going to be orange, 20% yellow, 20% green, and 20% purple. And now the question is that if you open a bag of Skittles and you don't get 20% red, 20% orange, 20% yellow, 20% green, and 20% purple, is the evidence in your bag strong enough to say that the manufacturer is lying and that's not the actual percentages? Or is your distribution of colors in your bag kind of different, but not different enough for you to make that conclusion? So what we're going to do is we are going to go down here and we're going to generate a sample of size, and we're not going to do 30, because if I ever got a party bag of Skittles and there was only 30 in there, I'd be rather disappointed. We're going to up this to 100. And one thing that this is going to do for us, we're going to set our sample size of 100. This is going to make our counts really easy to compare to the expected counts, because the expected counts are here in percentages. So if there's 20% of each, and we have a sample size of 100, well, then we should get 20 red, and we should get 20 orange, and we should get 20 yellow, 20 green, and 20 purple. That would be if we got the perfect bag of Skittles. Or if we did this over and over and over and over again, on average, we would expect 20 red, 20 orange, 20 yellow, 20 green, and 20 purple. So we're going to generate our sample. And as you can see, we did not get 20 red. We got 25 red. And we did not get 20 orange. We got 26 orange. And we did not get 20 yellow. We got 17. We got 18 green. We got 14 purple. Not one category ended up with 20. So is this strong enough evidence to claim that Skittles lies about the distribution of their candies? Or is this just random variation and we just got a bag that was slightly different, but not too different, slightly unlucky, but not so unlucky that we have evidence that Skittles is actually lying about their distribution? Well, to find this out, what we would do is we would do a chi-square test. So to do that chi-square test, and we'll just kind of show you the outer structure of the chi-square test today, and then next time we'll go reveal what's behind the curtain. But for right now, we'll start off with the begin analysis. And first here, you can see that we have a bar graph here, and this shows the frequencies for each category of Skittle here. So we have 25 red, 26 orange, 14 purple. So this gives us our categorical data in bar chart form, where the height of the chart is the count or the frequency of the number in each category. And this is what we're testing. So is this distribution here different enough that we don't believe that Skittles actually manufactures equal numbers of each candy? And then what we have down here is we have a nice little graph that shows the color, the observed count, and the expected count. And then in this last column, the contribution of each of these categorical values to the chi-squared. So we're not going to focus too much on this contribution here, but I just want to point out that we have the observed count. And that observed count, for example, red has an observed count of 25. That observed count is compared to the expected count. And then using a mathematical formula, that observed count and expected count difference is translated into what is called here the contribution. So orange has a higher difference. So it's going to have a higher contribution than red does. So you can see red has a difference of 5. Observed count is 5. Expected count is 20. Contribution ends up being 1.25. Orange has an observed count of 26. Expected count of 20. Difference is 6. Contribution ends up being 1.8. We're not going to focus too much on the formula there, but just know that the differences between the observed counts and the expected counts get translated into these contributions. And then you add up those contributions, and that gives you your chi-squared statistic. So now we have our chi-squared statistic. So what does that actually mean? Well, this gives us a measure of how extreme, how weird, how unlikely was this distribution to have come from a population that has equal numbers of red, orange, yellow, green, and purple Skittles. That gives us our unlikelihood. So now we just have to translate this into a p-value. And to do that, what we're going to do is we're going to build up our distribution of sampling chi-squared statistics now. So not a distribution of sample means, but a distribution of sample chi-squares. And for this, we're going to simulate. We'll start off with one sample and we'll add it to the dot plot just so we can build this up for this first example. So let's simulate that. And in the simulation, this sample was taken out of the population. And this sample actually has a chi-squared, you can see it right here, chi-squared score of 1.6. So that gets added to the distribution of sample chi-squared scores. And much like a distribution of sample means, we can simulate another sample. So you'll see this bar graph here change because this is sample number 1. There's sample number 2. And this distribution produces a chi-squared of 4.6. And that gets added to the distribution of sampling chi-squareds here. And then we can continue to simulate and simulate and simulate. And you can see that we are building up this distribution of chi-squared statistics from this population with every single new sample that we plug in there. With every single new sample that we take from this population, we can generate a new chi-squared score. And what we're going to do is, just so that we're not clicking this for the next 42 minutes, I'm going to go up here and I'm going to simulate 1,000 samples. So we're just going to speed run this. And I'm going to simulate 1,000 samples. And what this will do is it'll take 1,000 samples out of this population, calculate 1,000 chi-squared scores, and plot them all on this simulated chi-squared statistic distribution of sample chi-squares. So here we go. We're going to simulate. Boom, there it goes. And now we have 1,000 of these chi-squared scores taken from samples from the population of equally distributed Skittles candies. So now that we have this nice, almost looks like a curve here, this nice dot plot, we're going to plot the approximate chi-squared curve on top of it. So now you can see where the chi-squared curve comes from. And importantly now, we know how likely certain chi-square scores are. So you can see that scores between 1 and 3 here, those are very likely. to occur. And scores between 3 and 6, for example, those are also highly likely to occur. But once we get out here to 10, 11, 12, these scores are much less likely to occur. These are much less, these are much rarer scores to get. You need a sample that is really weird from the null hypothesis population, from that population of equally distributed Skittles. You need a population that's really weird in order to get a distribution of a sample distribution that's really weird to get these extreme chi-squared scores. But these are the chi-squared scores and the frequency that we would expect them to come out of this population. So now we can ask ourselves, well, if this is the distribution of chi-squared scores that we can expect coming out of this population, we'll go all the way back up to our original sample here that we generated. And we can say, well, how unlikely was this sample to have occurred? And the chi-squared score for that sample was 5.5. So let's enter that in to this area here, count the number and percent of dots greater than, that is, more extreme or equal to that chi-square scored of 5.5. And if we count, we can see that all of these dots here are equal to or greater than the chi-square scored of 5.5. So these are all samples that had weird distributions of colors that were as weird or weirder than the sample that we got. And we can see here that there are 261 dots, that is 25.6% in the selected region. So we have a 25.6% chance that this weird bag of Skittles that we had, where not a single color had a score of 20, not a single color had a count of 20, that bag will occur, something that weird or weirder will occur 26% of the time. So about a 1 in 4 chance of getting a bag that extreme. And I would not be willing to call up Skittles and tell them that their manufacturing process is a lie, that their distribution is a lie, if I only had a 1 in 4 chance of being correct. That's a pretty huge accusation to make when you have a 1 in 4 chance of getting something that is that weird. And that's kind of the basis of how you would use the chi-square test in a significance test. So that was a random sample that we generated. But what about something a little bit more extreme? So we're going to go down here to edit inputs. And we're going to change this red count here from 25. Let's say that we got a bag and there was only 8 red Skittles in the bag. And if red is your favorite flavor, this would be catastrophic. This would be a bad day. You open up your bag, you only get 8 red Skittles. That's horrible. And let's say that we get 20 orange and we get 22 yellow and we get 24 green and we get 26 purple. So everything else is kind of where it needs to be, but we only get 8 of those red. Is this now weird enough that we would be confident in calling up Skittles and saying, hey, something's wrong with your machines or you're lying to us about the distribution. Where are my red Skittles? This bag that I got, this sample that I got, that I bought from the store, has allowed me to conclude that it does not belong to a population where there are equal numbers of red, orange, yellow, green, and purple. So can we make that conclusion with this particular bag of Skittles? Well, let's begin our analysis. So there is our bar graph, our histogram of the distributions for red, orange, yellow, green, and purple. And as you can see, red is really, really low. And then here, once again, we have our category color, observed count, expected count, and contributions. And you can see here that orange, because its observed count and its expected count are exactly the same, it makes a contribution of 0 towards the final chi-squared score. But most importantly, look at that difference here. 8 is what we actually observed in our bag of Skittles. 20 is what we should have had. So that is a large difference in the expected and observed count, leads to a contribution of 7.2 towards the chi-squared score. And when we add them all up, we get a chi-squared score of 10. So now we have a new sample that is really weird. It gives us a chi-squared score of 10. So you can see a higher chi-squared score because it's weirder than our previous sample. And now we're going to figure out, well, where does this belong in the sampling distribution of chi-squared scores, or in the distribution of sample chi-squared scores? So to do that, we're going to go right ahead and we're going to simulate 1,000 samples from the null hypothesis population from that equal number of colors population. So we're going to simulate. And this is our 1,000th simulation that gives you a chi-squared score of 4.5. But importantly, here are the other thousands. Each sample produced a chi-squared score. Each sample produced a dot on this simulated chi-squared statistic. We have our density curve for the chi-squared distribution, this curve right here. But importantly now, we have a chi-squared statistic for our sample that we actually got in our bag, and that chi-squared statistic is 10. And if we pop that down here and we count, we can see that there are only 34 dots. There are only 34 samples in our 1,000 sampling distribution here. There are only 34 samples that got chi-squared scores 10 or greater, that were as extreme or more extreme than the sample that we got. And what that means is that there's only a 3.4% chance that our bag came from a population where the colors were equal across all of the colors. So only a 3.4 chance that our bag comes from a population where all the colors are equal. That makes it highly likely that our bag came from a population where the colors are not equal. And now you would have a lot more confidence calling Skittles up and saying, hey, what's going on? You said there's equal numbers of every single color. Well, I got a bag here that would only have a 3.4 chance of coming from such a population distribution. So I'm calling shenanigans. I'm calling you out. Where are my red Skittles? All right, so that was the Skittles analysis. Now let's very quickly take a look at the promised Froot Loops analysis. So I have been told that Froot Loops are actually the exact same flavor for every single Froot Loop. I don't know if that's the case. You can let me know in the comments below. But let's take a look now. We'll do a new analysis for Froot Loops just so we can see it for a different situation here. So for this, we're going to choose the Froot Loops distribution. And for the Froot Loops cereal, they claim that it also contains equal percentages. But this time we have 6 categories. So 16.67% each of red, orange, yellow, green, blue, and purple loops. So we can now do the same kind of analysis that we did for Skittles, but this time we do it for Froot Loops. So once again, we are going to generate a random sample size of 100, just again because it makes it easier to kind of visualize what the expected counts should be. So if we are expecting 16.67% each of red, orange, yellow, green, and purple loops, then in a sample of 100, in the long run, we would on average get 16.67 red loops in a box, 16.67 orange loops in a box. And again, it's fine to have that 0.67 there because this again is a long run average if we open box after box after box after box. Now, what happens when we open up just the one box? Well, let's generate that sample. So we open up one box and we see that in this sample, we got 17 red, we got 11 orange, we got 15 yellow, we have 16 green, we got 23 blue, and we got 18 purple. So notice that this is a case where not one of the counts actually matches the expected count. And that's because it would be impossible for the count to match the expected count. It's close, but you're not going to get 0.67 of a Froot Loop in a box of Froot Loops. I guess technically you could because some of them get crushed, but I digress. All right, so this is our sample of Froot Loops. Does this sample actually come from a population of Froot Loops where every single color has the same frequency? Every single color is produced in the same amount as every other color. So to take a look at that, we're going to begin our analysis. So once again, here is our histogram or bar graph of the count for each color. So we have 17 red, 11 orange, 15 yellow, 16 green, 23 blue, and 18 purple. And again, if they were at equal numbers, we would expect all of these bars to be exactly the same height. They're not the same height, but the question again is, are they different enough for us to call up Froot Loops and say, hey man, what's going on with the color of your loops? Which is a sentence I never thought I'd say. All right, so once again, we have the categorical value, the color, observed count, expected count, and contribution. Notice that the expected counts are all 16.667. That again is what you would expect to get in the long run. That is the average number of Froot Loops that you would expect to get in a box of 100 Froot Loops. And then here in the observed count, we have the numbers that we actually got in our sample of 100 Froot Loops. And then the observed count minus the expected count and then some other mathematical shenanigans gives us the contribution. Importantly, the further away the observed count is from the expected count, the larger the contribution is. And then you add up all those contributions and you get yourself that X statistic, the chi-squared statistic. Do not call it the X-squared statistic. It's the chi-squared statistic. Okay. So this time we're not going to go through the whole process of building up sample by sample by sample, the distribution of sample chi-squared statistics. We're just going to simulate 1,000 samples so we can get right to that distribution. However, I do highly recommend play around with this on your own, build it up sample by sample if you're having trouble following the logic and visualizing the fact that this distribution of sampling chi-squared tests that we're going to generate are just chi-squared statistics taken from the population, one sample at a time. And if you do it 1,000 times, you're going to get some very common samples, you're going to get some very uncommon samples, and that's where that distribution comes from. So let's go ahead and simulate that distribution. So this is the 1,000th sample. And as you can see, it has a chi-square test of 3.08. But more importantly, here are the other 999 samples here on this simulated chi-square statistic distribution of sample chi-square statistics. And we're going to plot the approximate chi-square density curve here. So there we go. So you can see that chi-squared curve, distribution curve that we were looking at before. And now we know which chi-squared scores from this sample of, from this population of Froot Loops are common, which ones are not so common over here. And now we can figure out where does our sample come from. So again, this is what we would expect our samples to look like. This is what we would expect our samples chi-squared statistics to look like if the null hypothesis was true, if every single color was equally produced. And now we take a look at our sample where every single color was not equally produced, and it has a chi-squared score of 4.64. So now we're able to determine, well, how extreme is 4.64? So we go down here and we're going to count the number or percent of dots greater than or equal to 4.64. So again, we want greater than or equal to because we want to know what are the chances of getting a sample this extreme or more extreme. So how weird was our sample? So we're going to count. And as you can see, 4.64 is right about there. So all of these samples here are samples that are as weird or are weirder than the Froot Loops box that we got. And as you can see, there are 458 dots in that region, which is 45.8% of all samples. So our sample is not really weird at all. Our sample is basically a 50-50 chance of getting a sample that far from the claimed distribution. So it's about 45.8% that we would get a sample that different from the claimed distribution. And again, this is a coin flip almost, whether or not our sample comes from the claimed population, whether or not our sample comes from the population where all colors are produced in equal percentages. So again, we have no evidence here whatsoever that our box of Froot Loops is weird in any way. It's basically a chance, a coin flip, whether or not it came from a population of equally colored Froot Loops. However, what if we didn't get this sample? Let's edit those inputs. What if we got something that maybe is a little bit more extreme? And actually, what if we got something that doesn't really look that much more extreme? So let's take a look at a box where we get 12 reds. We get 20, not 120. We get 20 orange. We get 13 yellow. We get 15 green. We get 12 blue. And then we get 28 purple. So we can see here that this is not that far off from the numbers that we had before. We got a couple of extreme ones, but it doesn't really seem that much more weird than the distribution that we had before. But let's begin our analysis for this one here. And you can see here we have our bar graph histogram distribution here of the different frequencies for each color, now with purple all the way up to 28. We have, once again, our table here of the color observed count, expected count, and importantly, contribution. And we can see that that purple count of 28 is given the highest contribution here because it is the furthest away from the expected count. So we total up all the contributions, we get a chi-squared score of 11.96. And now we can ask ourselves, well, how unlikely is this distribution to have occurred? How unlikely is it to get this few red, yellow, and blues and this many purples in our box of 100 Froot Loops? So to answer that question, we're once again going to simulate 1,000 samples so that we can get that distribution of sample chi-squared statistics from the null hypothesis. And now we take our chi-squared score from our sample, 11.96. We pop it in here, and we're going to count the number of boxes of Froot Loops with that would be greater than or equal to that chi-squared score. And as we can see, there are only 28 dots, only 28 boxes out of the 1,000 boxes that we opened had a distribution that was as weird as ours, or weirder, as weirdness measured by the chi-squared statistic there. So we only have a 2.8% chance of getting a box as weird as our box or weirder. So again, this would be very strong evidence that our box did not come from the null hypothesis population. It did not come from that population where the colors are produced in equal amounts. It comes from a population where purple is way more frequently produced than the other categories. And we would again have confidence calling up Kellogg's and saying, hey, you guys are lying about your distribution of Froot Loop colors, or something is very wrong with your manufacturing process. You need to check your machines. We would be justified and have the statistical backing to make that claim and present that evidence and maybe get to the bottom of this Froot Loop conspiracy. All right, so that was Froot Loops. Last one we're going to do here is we're going to do M&Ms. So the reason that I really wanted to get to M&Ms, not just because I love candy and we just keep doing this candy themed examples, but the reason I wanted to get to M&Ms is because so far we have been dealing with expected or claimed distributions where the distributions were equal. So for example, Froot Loops. Froot Loop cereal claims that it contains equal percentages, 16.67% each of red, orange, yellow, green, blue, and purple loops. And Skittles claims that they contain equal percentages, 20% each of red, orange, yellow, green, and purple. But what about a distribution where they don't claim equal percentages in each category? Can we use a chi-squared test to analyze those populations and those distributions? Well, the answer very wonderfully is yes. And we're going to introduce that or demonstrate that by taking a look at M&Ms. So for some reason, and if somebody knows the answer, please let me know in the comments below. For some reason, the Consumer Affairs Department claim about the distribution of color for M&M's milk chocolate candies produced at its Hackettstown, New Jersey factory. So this is very, very specific. These are the percentages. So as you can see, brown, red, yellow, and green are produced in equal percentages of 12.5%. But then for some reason, orange comes in at 25%, and blue also comes in at 25%. So that's their claimed distribution. And this is the first case that we're seeing at where a claimed distribution does not have equal distribution across all categories. In fact, this one has double in both orange and blue than its other categories. So can we use the chi-squared statistic to analyze deviations from this distribution? Well, the answer is yes. So let's get straight to it. So once again, we're going to generate a sample size of 100 M&Ms. So let's generate that sample. And as you can see here, we have 12 brown, 13 red, 13 yellow, 12 green, and then we have 31 orange and 19 blue. And we expect to get more orange and blue because those are supposed to occur at higher frequencies. So is this sample coming from this population of this distribution here, this population with this particular distribution, or is it weird enough for us to call up M&Ms and say, hey, something's wrong with your manufacturing process, or you guys are just straight up lying to us? So let's begin this analysis. And here we have our distribution histogram here, where it shows us the frequency or the count of brown M&Ms, red M&Ms, yellow, green, orange, way overrepresented, it seems, but overrepresented enough, we will see, and blue here at 19. So here we have the color, the category variable, the observed count, the expected count, and then its contribution to the chi-squared statistic. So you can see brown here, very, very close. Observed count was 12. Expected count was 12.5 because 12.5% of M&Ms are brown M&Ms. Very small contribution to the overall chi-squared statistic. Same here for red. Red came in at 13, expected count 12.5. Notice exact same contribution as blue because it's the exact same difference between the observed count and the expected count. And then you can see down here, orange and blue also making their contributions to the chi-squared statistic. So now we need to know, well, we have a chi-squared statistic of 2.96. That's the measure of weirdness for our sample. So where does this put our sample in the distribution of sample chi-squared statistics? So to find that out, we're going to simulate that distribution of chi-squared statistics by simulating 1,000 samples coming from the null hypothesis distribution that has this particular distribution here. So again, not equal across categories, but double the amount of orange and blue as the other categories. So let's simulate those 1,000. We'll hit simulate right here. This is the chi-square test for this sample, the final sample in our 1,000 samples that we drew, but from the population. But importantly, here are the chi-squared statistics for all 1,000 samples. So you can see that we have a lot of samples coming in with chi-squared statistics 6 or lower. We have very few samples coming in with chi-squared statistics of 16 or greater. We're going to plot that chi-squared density curve so you can see what that curve looks like on top of our simulated data. And now we have a basis to compare how weird is our sample. Because if we take out 1,000 samples from this null hypothesis population, if we take out 1,000 samples from the distribution that M&Ms claims to have, these are the chi-squared statistics and the frequencies we would expect. So where does our chi-squared of 2.96 fall? Well, we would go down here. We're going to count the number and percent of dots that are greater than or equal to, i.e. as weird or weirder than our sample. And we hit count, and we can see that there are 676 dots, or 67.6% in the selected region. That means that the number of, or the percentage of samples coming from this null hypothesis population that are as extreme or more extreme than the sample that we got, that is 67.6% of samples. So we have a very typical bag of M&Ms here. We have a very typical bag of M&Ms. This is what this is saying, because our bag of M&Ms is less weird than 67.6% of all bags of M&Ms. So this distribution here, even though it kind of looks like orange is just skyrocketing off into the top, there's way too many orange. That is a distribution that would occur 67.6% of the time. A distribution that weird or weirder occurs 67.6% of the time. So we have no evidence whatsoever to call up M&Ms and say, hey, we would call them up and say, hey, you know what? I'm pretty sure you're doing a fine job and producing exactly the distribution that you are claiming. So let's go back here and do our, well, but what if we got a distribution that looked more like this? So what if we got a distribution where we only had 6 brown M&Ms and we had 19 red M&Ms and we had 8 yellow, 17 green. Instead of 31 orange, we only had 30, so not much of a difference. Instead of 19 blue, we only had 20, so not much of a difference. So you can see that the orange and blue stayed exactly the same, and just some minor deviation now in the brown, red, yellow, and greens. And let's see what this does to our analysis. So we'll begin our analysis. This is our distribution now. And visually, again, does this look weird enough for us to call up M&Ms? Very difficult for our human minds to make that determination. But as you can see here, now we have brown contributing a lot to the overall chi-squared statistic. We have red contributing a lot to the overall chi-squared statistic. We have yellow and green now contributing more to the overall chi-squared statistic. So we go on and we sum up all those contributions. We have a chi-squared statistic of 12. And now, again, that is the measure of weirdness for our sample. So is that weird enough for us to call up M&Ms? Well, let's simulate, again, 1,000 samples. So we'll hit simulate. This is the chi-squared statistic for the 1,000th sample. We go down here and see our distribution of chi-squared sampling statistics. And we are now going to count the number and percentage of dots greater than or equal to our sample chi-squared statistic, which is 12. And we hit count. And we can see that there are only 35 dots, only 35 samples out of the 1,000 that we grabbed have a chi-squared statistic of 12 or greater. That's only 3.5% in this region, which means that our bag has a 3.5% chance of coming from M&M's claimed distribution population. So we have a very small chance that it comes from the claimed distribution population, which means we have a very large chance it does not. So at this point, we can call up M&M and say, hey, you sold me a bag and I had way too few browns and I had way too few yellows and I had way too many oranges. And we would, again, have confidence in making that assertion. Now, this is a nice segue into our final example here, because way too few browns can actually be quite dangerous in the wrong circumstance, in the wrong situation. And one of those situations is comes from a story about the band Van Halen. So Van Halen is infamous for not allowing any brown M&Ms to be in the backstage area. And if they found one brown M&M, they would throw a fit. So Van Halen was a rock and roll band, huge in the 80s, huge in the 90s, revolutionized rock and roll music. And one of the things that they did is they had these massive stadium tours with very complicated pyrotechnics and electrical equipment that needed to be set up, broken down, set up again and again and again, performance after performance after performance. And one of the things that they did as part of their requirements for their shows is that they insisted that there be M&Ms backstage available to them. But they also insisted that there should not be one brown M&M in that backstage area. And we are now, and that became kind of the stuff of legend in terms of, well, maybe they're just rock and roll divas, or maybe there was something more behind this. So now we're going to get the answer from their lead singer, David Lee Roth, as to why they had that particular stipulation. And then we're going to use statistics to see if it was an effective way of achieving their goal.
How many times have I been emailed or tweeted or everything in between as to what is the real story about the brown M&Ms? Many years ago, it was part of the Van Halen contract as we toured through the arenas in the 80s that there would be no brown M&Ms found in the backstage area, or the promoter would forfeit the entire show at full pay. This was touted wildly and widely as simple rock star misdemeanor excess and being abusive of others simply because we could. And who am I to get in the way of a good rumor? Please come in, sit down, make yourself at home. I did. In fact, the reality is quite different. Van Halen was the first to take 850 par lamp lights, huge lights, around the country. At the time, it was the biggest production ever. And we would have structural, physical issues because, hey, there wasn't the proper electricity, load bearing, stress, etc. So, in the middle of a huge contract rider, in the very middle of it, I had them place a clause. that just out of the middle of nowhere, it would say, for example, there will be 12 ampere high voltage sockets placed at 15-foot intervals, not to exceed the load bearing, et cetera, and then just out of the middle of nowhere said there will be no brown M&Ms in the backstage area, or the promoter will forfeit the show at full price. What was the point? If I came backstage, having been one of the architects of this lighting and staging design, and I saw brown M&Ms on the catering table, then guaranteed the promoter had not read the contract writer, and we had to do a serious line check, because frequently we had danger issues or accidental issues and so on.
All right, so the brown M&Ms were actually a safeguard to make sure that the instructions for their electrical equipment was followed out correctly. So what we're going to do now is we are going to do an analysis to see how effective was that safeguard in making sure that the instructions were followed. In other words, what would be the odds? What would be the chances? Is there a chance of filling up a bowl for a backstage area when you're catering a rock and roll band, filling up a bowl of M&Ms and just by chance not getting any brown M&Ms? What are the odds of that occurring? Well, that is a question that is perfect for the chi-squared test. So what we're going to do is we're going to go back up here one more time. We're going to edit our inputs. And this time, instead of 100 M&Ms, I did a little bit of research. And if you were going to fill a 3-quart bowl full of M&Ms, you would end up with 2,520 M&Ms. So that is going to be the sample that we are going to generate here. So that would be you just tearing open bag after bag after bag, pouring them into this 3-quart bowl until you filled it up, 2,520 M&Ms. So let's generate that sample. And as you can see, this is the amount of M&Ms that we would expect that we would get if we did one sample of this 2,520 M&M bowl. What we're going to do is we're going to edit these counts here so that we are going to get 2,520 M&Ms, but we're going to get 0 brown M&Ms. So we're going to put 0 here. And then using the expected counts, I calculated that if the distribution for the other M&Ms still followed the same pattern of orange and blue being twice as many as red, yellow, and green, we would end up with 360 red, 360 yellow, 360 green, 720 orange, and 720 blue. So that would be the expected distribution, or that would be as close to the expected distribution if there were no brown M&Ms in this particular sample. So what are the odds? What are the odds of getting a distribution this close to the expected counts? So I made the expected counts as close as possible while still maintaining 0 brown M&Ms. And what this is going to show us is going to show us the odds that Van Halen would go backstage and not find any brown M&Ms, even though the promoters did not follow their instructions. So was this a good way of them ensuring that they did not have any electrical problems? Well, let's start that analysis. All right, so here we have our frequency distribution, our bar graph, and as you can see, absolutely no brown M&Ms. We get red, yellow, and green, and orange and blue in exactly the proportions that we would expect in the long run. And then here we have for the brown M&Ms, an observed count of 0, expected count of 15, huge contribution to the chi-squared test. The red observed count compared to the expected count, you can see it's not exact because we did have to account for the expected count in the brown M&Ms here. So there's no way to make it exactly alike, but you can see that the contribution here to the overall chi-squared score is rather small for those colors as well as orange and blue. But we end up with a chi-squared statistic of 360. So to see if that observed chi-squared statistic is unusual, let's perform those simulations. So we're going to simulate 1,000 samples. And again, that's our 1,000th sample with a chi-squared of 5.554. And importantly, here are our 1,000 samples, our 1,000 samples of 3-quart bowls of M&Ms and their chi-squared statistics. So we can see that the number and percentage of dots equal or greater to, what was it? 360 was the chi-square test. If we count that, we can see that there are absolutely 0 dots in the selected region. And if we bring this up to, let's say, 10,000 instead of 1,000, and we simulate that, it might not allow us to do it. Let's see if we, oh no, there it goes. If we simulate that now, you can see that we still have absolutely 0 dots in the selected region. That means that Van Halen could do 10,000 concerts and they would not once end up by chance with a bag of M&Ms or a bowl of M&Ms where there were no brown M&Ms, just by random chance, just by the chance occurrence of not having brown M&Ms in your sample. That was basically a 0% chance of happening. So what this is telling us statistically is that this is a very, very effective way of making sure that they read the writer, because there is in effect a 0% chance that you would just by random variation end up with a bowl of M&Ms without any brown M&Ms in it. So again, this was a ingenious way to protect themselves from this occurring, and we have now used the chi-square statistic to prove that it actually was effective, kept them safe. 10,000 concerts, not once would they go backstage and end up with a bowl of M&Ms just randomly without a brown M&M. So if they went backstage and they saw a bowl of M&Ms and they did not have a brown M&M in there, no chance whatsoever that it belongs to the regularly distributed M&M population, which means that there's a super high chance that it belongs to the no brown distribution M&M population, where somebody actually took those M&Ms, those brown M&Ms out because they read it in their writer, kept them safe, no explosions. Thank you, statistics. Thank you, chi-squared. All right, so that is all for what I wanted to do today to introduce the chi-square test for goodness of fit. Hopefully it allowed you to wrap your mind around what the chi-square test actually is and what it's been used for. Next time that we meet, we're going to unleash SPSS on the chi-squared statistic to do the calculations, and we're going to apply it to actual psychology studies and see how it's been used in the past to make psychological conclusions about populations. But that is all that I wanted to cover for today. So until next time, see you later.